Newton's second law as described by the motion of a skateboard. I'm Bennett Alterman. So the objective of this lab is to simulate how Newton's second law is applied by observing an object in constant motion. So what this means is an object with no change in either velocity or direction. So what I did was I took a skateboard and rolled it across the ground, and that was my model. So what I've done is included my system of a skateboard and the earth. How I've set up my axes are as follows. The positive x-axis is to the right, while the negative x-axis is to the left. The positive y-axis is up, and the negative y-axis is down. I've also included a length bar of 1 foot, which is equivalent to 0.305 meters. So including all of the forces and interactions at play here, we have gravity, kinetic friction, and normal force. And if you'll see my free body diagram below, you'll see that as the skateboard moves along the negative x-axis, or to the left, there is a gravitational force, negative mg, pushing down towards the earth or pulling towards the earth, and a normal force of the earth on the board pushing and going against this gravitational force, as well as a kinetic friction force which is opposing the direction of motion. So here you'll see my tracker video of what I've done. As you can see, the origin is on the right side of the screen, and the skateboard moves from the origin along the negative x-axis to the left. Here we have a graph of my tracker data. We have position, or x, on the y-axis and time, or t, on the x-axis. What you'll notice is a constant negative slope. So in terms of physics, what does this mean? Well, using Newton's second law equation of F equals ma, or more appropriately, V final equals V initial plus F net over mass times delta t, you see that F net is 0 due to a delta velocity of 0, meaning a constant velocity or no change in velocity. This is also applicable through the conservation of momentum, which is stated as delta momentum, or the change in momentum, is equal to the net force times delta t. And again, in this case, it is 0 due to the constant slope, meaning 0 acceleration and 0 change in velocity. So what I've done here is I've made a computational model similar to what we used in the first week's lab. What I've done is I've taken the mass of my skateboard to be 3.18 kilograms. I also have the initial vector position at 0, 0, 0, or the origin, as well as the initial velocity of negative 2.309, which I took from my tracker data. I also have a delta t of 0.0333, which again is an average of the time change in my tracker data. My total time of the video is 1.233 seconds. Both the F net vector and the ball velocity vector do not change in this experiment, so they remain at 0, 0, 0. The ball position vector has a change in position of negative 0.0767 in the negative x direction, which again I took from my tracker data, finding the average difference between each change in position. So here I will run the code. You see again that the skateboard is represented by a ball moving in the negative x direction from the origin, and again looking at the graph you'll see that I have similar results to what I've previously shown from my tracker data. Sorry, here it is again in case any of you missed it. Now, combining both my skateboard and my actual model, you can see that they line up almost exactly. So, does this model accurately predict what we saw? The answer to that question is relatively. Why, you might ask? Because the model doesn't account for both the friction force, which is a kinetic friction, or the gravitational force, both of which can act to change delta V to be non-zero and give a slight negative acceleration. So what happens again if I change the axes of these graphs? Well, quite frankly, nothing. The relationship between time and position is not changed by the orientation of the axes. Overall, the result of this experiment was successful, and I am happy with how the model matched the actual observed experience.